Let us find the inverse of this stubborn matrix. First, I don't like the decimals, so I'll write everything in fraction. Yes. So that's not too bad. I don't like fractions either, but you know, it is what it is. Now let's assume that this matrix has an inverse and try to proceed with Gaussian elimination. The way we do this is we augment the identity matrix to the original matrix that we have, and then we establish a public goal of, you know, transforming this form of the identity matrix to the other side. So we make these ones, and we make all the other entries be equal to 0. So let's do just that. To proceed systematically, we usually go row by row. Here I would like to start slow by multiplying by 2/7, because this would make things a little bit easier for me. Well, for you, I mean, I could do this. And this is very arrogant. I should not have said that. Half of 2/7 is 1/7. Okay. So that's not too bad, I hope. Now I can make zeros here by making some very smart choices. So if I multiply the first row by -10 and add it to the second one, this becomes a 0. If I apply the same logic and multiply the first row by -5/2, then the same thing happens. Then I should get something that looks like this. Oops. Yes. So here I should have zeros. And here I'm not sure yet. I still need to compute these values. To compute these values, I'll use my nice draft, which I have here. This is my nice draft. And I use it to minimize my mistakes. So fun fact, I have to do this video for the second time now, because I made a mistake even when using this draft. But you know, the draft really helps you not to make mistakes in general. You put this row here, you put in your scaling factor -10, and you scale by -10 now. -10 minus 20/7 minus 10/7 minus 20/7. See, I almost made the same mistake. There was also a change in sign. I kept recording for, I don't know, 20 minutes, and then I knew I reached an incorrect solution. So that sucks. Don't do like me. 20/7, not 70. And then the other two terms was just 0. I would like to add this to the second row. I get 0. -3 is -21/7. I get -1/7. 2 is 14 over 7, so this is 4 over 7. This is minus 20 over 7. I hate fractions. I think you hate them as well. Like, imagine hating to watch this. Yeah, that's not too difficult. Now imagine, having to record this. It's much much more difficult, much more intense. But I'm happy because I get to explain things to you, and you get to learn something. So this makes me happy. This is the good part for me. So I'm done with this second row. I apply the same logic and proceed similarly for the third row operation. So this is not difficult, it just takes time. I would like to add this to the third row. And so I do this, I add the second and third values. Three over 2 is 21 over 14. Sixteen over 14. 7 over 7. And this is 0 as expected. So 2 over 7. 16 over 14. Minus 5 over 7. 0 and 1. Yeah, this is not too bad. 16 over 14 I can write as 8 over 7. Okay. And now, since everything is divisible by 7, well, not divisible by 7, everything is being divided by 7. So I'll just ignore that, that factor. And I will now try to make some zeros here and there. So let's do that. To do this, I will multiply by minus 2. And here I will multiply by 2. I would like to take a moment to check that the first step was correct, because if it's not, that would be very problematic. This is actually funny. I found a mistake. It is right here. So before I was multiplying by minus 2, I was multiplying by minus 5 over 2. And it turns out it's a problem with the sign, 5 over 7 minus 7 over 7 is minus 2 over 7. It's not 2 over 7. So I'm glad I was able to save that, because if I hadn't, I would just spend more time recording, and that would not be so good. So maybe when it involves lots of fractions and lots of changes of signs, you should probably give it a second look. Always give it a second look. Okay, so now I proceed and I multiply by 2. I multiply the second row by 2. Here's the second row. And here's the multiplication by 2. Now let me write the other row, which I'm adding this multiple of 2. This is even more interesting. The factor is going to be minus 2 because I chose this factor when I wanted to make this a 0, but this was not minus 2 over 7, it was 2 over 7. So 2 would make it 0, but minus 2 over 7 would need a minus 2 to make it 0. I hope this is clear. So I do this, I just switch the signs. And this is great because I'm also multiplying by minus 2 in the other one. So I don't need to do this twice. Now, which other row am I adding this to? It's the third one. This looks interesting because I see that we have now 3 zeros, right? 0, 0, 0. And here we'll get 35 over 7 minus 2 and 1. 35 over 7 is 5. Anyway, it looks like we might not need to multiply upwards, because if I just write this down and I write zeros, then I can no longer achieve my intended goal of making this look like the identity matrix, because I have a row which is full of zeros, at least on the left hand side. And this is enough to stop here and say there is a problem with this matrix. It does not have an inverse. So I write this down now. We have a row full of zeros. So A does not have an inverse. And finally, to check this, and there's a very nice check for this, which is the determinant test, which tells you that if the determinant of A is equal to 0, then A is, well, I would say even, I think it's if and only if A inverse does not exist. So there's no inverse. Or you could say A is not invertible as well. So these are all vocabulary you can apply. Now give me a moment, I will set up my calculator to compute the determinant now. I'm back, and here's my calculator. In the exam, obviously, you can stop here and say that there is no inverse, but here we are doing our due diligence by computing the determinant. As you can see, these are exactly the values which are inside of the matrix, and the determinant when computed is 0. So this matrix really doesn't have an inverse. So this is more or less another proof. I don't think this is obvious. If you would look at a matrix like this and you make a small mistake with the sign, you would probably get a completely invertible matrix. And it doesn't look like the vectors, the row vectors are linearly dependent in any way possible. So it's really hard to tell. But what can we do? And it is what it is. So in short, if the Gaussian elimination process fails, in the sense that you no longer can achieve this pivot of ones with zeros everywhere else, then you know that there is no inverse. The moment you cannot achieve this, you know that this matrix is not at all invertible. And that is pretty much all I want to say for this very specific part. Always remember, not all matrices, in fact, many matrices do not have any inverses at all.